Alright, today I'll be doing problem 7.43. Take a minute, figure out how you would do it, and then if you have any questions, watch me do it. Alright. Hopefully, if you didn't solve it all the way, you at least have some idea of how to do it. It's not a very difficult problem. You just need to understand what the equations mean. Okay. I think that the picture in the book is confusing, because they basically try to cram 3 pictures into one, so I'll draw 3 pictures. First is when the spring is compressed, and we have spring okay, that is compressed up against the block. Block of mass M. And that's the initial state. And you want to think what kind of energy or work is being done at this point. Well, this is no energy because it is no kinetic energy because it's not moving. But the spring has potential energy. So just something to think about whenever you're drawing a problem with a spring in it. Okay, second picture. Is when the spring is fully extended. Right. So now the spring has no potential energy. It's fully extended. All the potential energy that was in the spring is now in this block, which is moving this way. It has kinetic energy. And then the third picture is when it comes to rest. We still have the spring, not that it's relevant anymore, but it's still fully extended. And the block is, let's say, over here. And the block is not moving, so the block has no potential energy because it's not, raised up in the air, it's just sitting on the table. And it has no kinetic energy because the problem says it's at rest. So that will allow us to make our equation correctly. Alright, so what do we know? We know at the beginning it doesn't have any kinetic energy, so we're going to be using this equation. Well, I'll leave that out for now. Explain why I put it in later. Equal to kinetic energy final. Let's make that initial. Make this final. And U final. Well, we know it's at rest on a tabletop. So if it's at rest, in the end, it has no kinetic energy because it's at rest, it's not moving. And we know it doesn't have any potential energy because it's just sitting on a table, it's not floating in the air. It's also not compressing the spring, so there's no potential energy stored in the spring either. So this side is 0. At the beginning, what do we have? Well, we have all the potential energy stored in the spring, so that's something. This is nothing. Well, we can't really have U sub I equal to 0 because we know U sub I is actually something. It's greater than 0. There's some potential energy stored in the spring. So we're missing something. And this is a good time to remember that the problem gave us, wants us to find, actually, mu sub k, which is the coefficient of kinetic friction. So we have actually lost some energy to friction, and that is why it comes to rest on the tabletop. It's because it lost that energy to friction. So instead of this equation, this is not right. We're missing something here. So instead, we'll have K sub I plus U sub I plus W other, some kind of work. In this case, it's friction. It's equal to K sub F plus U sub F. This is just what we want to find. Don't need to leave that up there. Okay. But everything we said earlier still applies. This is 0, this is 0, this is 0. So U sub I plus W other is equal to 0. That makes sense, right? Because we had the potential energy stored in the spring, and then it pushed it, converted it to, it pushed the block, right? Converted it to kinetic energy, so it slid, and then came to rest, just completely stopped. So friction slowed it down and converted all of that kinetic energy into, heat, sound, whatever, due to the friction. Okay. So, now that we know that, we can just say 1/2 K sub S, that's the spring constant, right? I'm not working with numbers in this problem because, if you want to understand how the problem works, then you should focus on units and on solving it symbolically. You can check your symbolic equations by looking at the units to make sure they're okay. You don't get a time in what was supposed to be a time turns out to be something meters per second. That's a good way to check your symbolic equations. But I'm just going to solve it symbolically. Okay, x squared, that's the distance that the spring was compressed, is equal to, skipped a step, just mu sub k times the normal force, right, which is just m times g, and then times the distance that it traveled, because that's force over distance, which is the definition of work. So we're good. And we know it equals 0. Then we just solve for mu sub k. Do a little algebra. Okay, thought I wrote it wrong for a minute. And there you go. So just to review, we found the coefficient of kinetic friction, mu sub k, and by just having the initial potential energy, which is this guy, all we had was the initial potential energy and the final state of the two objects. And from that, we found mu sub k, which, in my opinion, is pretty cool. But we had the spring constant, k sub s, and the distance that the spring was compressed. We had the mass of the object, gravity, obviously, and the distance that the object actually traveled. So from those, we found the coefficient of kinetic friction. This kind of problem is really, you just have to think what you know. You start out with some energy, right? And you know that in the end, you don't have, the energy is gone. It went somewhere. It didn't just disappear. So, it had to go to friction in this case, because energy can't just disappear. It has to go somewhere. So anyway, hope that was helpful.